and I use machine learning for my thesis. And today we will a couple of different concepts about machine learning, and it's an introductory course, and we will go over Python's scikit-learn packages. So just to briefly go over some of the things that we will do. Last week we talked about only machine learning, and now this will be the application. But basically what we want to do is two things. When we have a data, we would like to either find the underlying groups in the data, or we would like to predict the targets if we know what the targets are. So based on those two things, maybe you have been familiar with some of the terms. If you want to find the underlying groups in the data, that's called unsupervised learning, and the clustering methods or dimensionality reduction methods go under this. And if we want to predict the targets, if we want to make predictions, whether it's a class information or any kind of continuous value, it would go under supervised learning. And the two main concepts are classification and. So today I will briefly go over a couple of different algorithms, all of these different aspects, and how to use learning in order to test our model. So we will be talking about different kind of models and different kind of tasks. So this is just a brief summary of what machine learning is, and I will not go into detail about it. And in this tutorial, we will learn about all of those. Okay, so since this is, we have a couple of different packages. So what I would like you to do is to import matplotlib in order to plot some of the things that we will visualize. And I'm using NumPy and pandas in order to load and manipulate my data. And then this, there will be various different functions that I will use from the scikit-learn module, and I will be importing them when I'm applying those functions. So I'm just going to run this. Okay. So we will mainly talk about the iris data set, and we talked about it last week, but essentially the iris data set is a data set that consists of 3 different species of iris flower. It's a purple flower, and they have 3 different, I've said it before, 3 different species, and they can be differentiated from each other based on 4 different features. And we will learn how to differentiate these features, and they look very similar to each other if you're interested in looking at them. It's pretty difficult to also look at by eye. Okay, so the feature relationship of these 4 features and their correlations. We will learn how to do dimensionality reduction using principal component analysis, but it won't be that necessary for this data set. It's just for us to learn. And then we'll learn how to scale the data. And then we'll apply clustering and classification algorithms. And then we're going to compare this to another image data. So we will first focus on flowers and then handwritten digits. So first, I'm using scikit-learn's datasets. So if you take a look at the documentation of the datasets function, there are a lot of different kinds of datasets, and I'm loading the data with this function called dataset. And when I load this dataset, it's in an object called scikit-learn's datasets, and it's really difficult to manipulate them. So I'm turning it into a pandas data frame. So what pandas data frame looks like is basically okay. So here we are loading the iris data. So with this data statement here, I'm just loading the data and the targets. And then the columns become the iris feature names and the targets. So, and we can see it here. So we have the 4 features and the names, and then the targets. The target will be 0, 1, or 2, depending on the 3 different species of the iris flower. And then with the iris df head function, I'm just displaying the first 5 rows of this data set. Okay, so this is what the data looks like. And if you just focus on the board for a minute, we have the data and we have known targets, so we can do supervised clustering. Feel free to interrupt me and ask me any questions you want along the way. Okay, so so what I would like to first do is that since we have 4 different features, I'd like to see how these features are, if they're correlated with each other or not. Because you might be interested in that too, and you might want to get rid of correlated features too. So here what I'm doing is that I have a feature, I want to create a feature correlation matrix, and I'm just defining it like that. And then I'm taking the feature names of the iris data set, and I have a small nested loop that goes over each of the pair of features, and then it just plots the correlation. So I also calculate the stats function. So I'm just calculating the Pearson correlation here. And you can do the correlations based on this. So let's see how the correlation matrix looks like. Okay. So here we can see that the diagonal objects are 1 because it's a correlation of the same feature by itself. And then here we can see that the sepal length and width are not correlated at all, but the sepal length and petal length are pretty much correlated. It's 0.87. So it's just a nice way to visualize if we have any redundancy in the data, because when we're working with high dimensional data sets, and if we have a lot of correlated features, we want to get rid of them because they will be dominating our decisions and can affect our decisions too. So it may not be very important for this data set, but it's a very important tool to just visualize what's going on with the data, with the raw data. Okay, so and since this is just not enough to see what the data looks like, here I have again the pairwise features here, just to see how they look like. So what I do here is that I define X and Y, and X stands for the data, and Y stands for the target. And I will mainly keep this format along the way. And then I'm coloring each of the different iris. Then this will create me an index of the colors. And then here I have 4 different subplots that I'm plotting each of the feature correlations together. And I'm not plotting the same feature by itself. It doesn't make sense. And I have all of the titles that I already entered before. So let's see how this looks like. Okay, so here we have 4 different features and 4 different pairwise ways of looking at it. And the colors represent the different species. And here we can see that with only using these 2 features, we can just visually see that there's some kind of a decision boundary. Like if we pass this line, most of them will be red. And then here we have some uncertainty because they're overlapping with each other, but still there's a good separation. And also we can see the same kind of separation with these, but then things become a little bit chaotic with these 2 specific features. So it's just we are not doing anything related to machine learning so far, but just to visualize what we have with the data. Okay. And this also tells us that what kind of, if you want to do a classification task, what kind of, so we would be getting a really high performance with this red species, but the others will be a little bit, can be misclassified. Okay, so once let's think that we have a lot of features. In this case, we want to reduce these dimensions into a lower dimension. So what is mostly used is a technique called principal component analysis. And what it does is that it combines the features in a linear way to reduce the dimensions. So it finds the direction of the highest variance, and then it transforms all of the data points on that. And it's doing this as many times as you want. So, and I'm using the scikit-learn decomposition function, and from there I can call the PCA function. For that, I have been saying that PCA is a linear combination of features. But what PCA stands for is principal component analysis. And here we need to define how many components we need to extract from this method. And in order to visualize what's going on, we usually have two components that we plot. And here, this is the first line that we're calling the model. So we just call it by its name, PCA, and number of components as 2. And then the lowercase PCA defines our model. And then we are calling that here with another function of PCA called fit transform. And what it does is that it takes the input data set, which is iris, and then it transforms into another kind of data set that we know that it will have only 2 principal components. So from 4, we can reduce it to 2. And this may sound unnecessary with this data set. Again, I would like to underline that this is important for high dimensions. So let's see how the principal components look like. And here I'm plotting the iris PCA data set here with the first and second PCs. And I'm again coloring the different species. So here, this doesn't look better than what we have been seeing before. But again, we can get more information with larger data sets. So what we can do with PCA is that we can look at the correlations. What we do with PCA is that, as I've been saying, PCA looks for the highest variance in the data. And the most important thing is to extract from PCA is the explained variance in the data. So this may not sound that important, but let's walk over this next cell here. So here I'm again calling the stats function from SciPy, and I'm again defining a pandas data frame here, but it's just going to be okay. Let me just run this first. Okay. So what? Okay, sorry. So with the first 2 lines, I'm just printing the percent explained variance. So what it does is that we can call the PCA explained variance ratio method here, and this defines the first principal component in the beginning, and then it will call the second. And here we can explain 92% of the variance in the data by just using 1 dimension. So we take 4 of these features, and then we put it in PCA, and then we can explain nearly most of the variance in the data. So it's a really powerful tool. And then after explaining that much of data, the second principal component can only explain 5% of the variance. So this is cool, and this is something that, yes?
Is there any way to know how my remaining features contribute to PCA1?
Yes, so it's either, so you want to understand with, let's say, with PC1, kind of like relationship. Yeah, so that's what I use for, so that's what I'm showing here as the correlation. So because it's a linear combination, we can think of it as that way, right? So here, let's say I define PC1, and then it will be a linear combination. So I will have coefficients of the features. So I will just find C1 as the coefficient times F1, and this is my first feature. And then C to F2, and it goes on until how many features. But these coefficients by itself does not mean anything or negative, depending on how you're doing linear transformation into a space. But what we do in order to explain which features are dominating which principal component is to look at the correlation. So this is what I'm showing here. So if you look at the first row, with the loop here, with the second, with the nested loop inside, I'm just piercing correlation between the principal component and each feature. So here we can see that with PC1, petal length and petal width have really high correlations, and petal length has 0.99 correlation. So we can say that petal length importance in PC1. And then as well as petal width and sepal length. And then in PC2, we can see that the sepal width has more as much in the principal component 1. So it's just a way to understand that relationship.
You don't say like how much percentage of PC1 what they are, you say how they work. That's the way.
I mean, this it's just if the question is to understand the principal component, this is the way, because the coefficients themselves, of course, as long as they're not close to 0, but they can be positive and negative, right? So the coefficients themselves can also mean something, but it's just because they don't have a fixed unit or fixed sign, it's hard to understand, right? Like if you have, let's say, for these two coefficients, if you have 0.5 here and minus 0.5 here, it's really difficult to say which one is more important or not. So yeah, this is just a, maybe it's not a very explicit way of understanding that relationship, but it certainly tells you something. Okay, so that's so this is why I call this as interpreting features from PCA. Okay, so far we have learned that correlations between features are important, and we can reduce a higher dimension of features using principal component analysis. Okay, so for some of the data sets, we may want to scale the data. Let's say we have a lot of features. A couple of the features are measured by, let's say, in meters, and a couple of them are measured in millimeters. And if we put all of these data together without doing any kind of scaling, the larger number of features will dominate our learning, and also they will corrupt the algorithm as well. So what we want to do is that we would like to have the same kind of unit in all of our features. So with the so that the iris data set all has the centimeters as the feature unit, so it's probably unnecessary to do scaling in this sense, but just for us to learn. So in order to do that, I'm calling the pre-processing function from scikit-learn package, and I'm again defining the data as x and target as y. And then when I want to scale the data, I'm just calling the pre-processing function and standard scaler. So you would like to do other kinds of scaling too. But what standard scaler will do is that it will take the feature and it will transform it into, it will scale it to 0 mean and unit variance. And then with the fit and transform function, I'm taking this data set and I'm transforming it in one line. Sometimes, so this will just produce us a data set and it won't have an output. But sometimes what we like to do is that we would like to scale the data by using just a subset of the data. Let's say that we have, if you think of it as, let's say we have a data that we have healthy individuals and individuals with a genetic disorder. And we would like to basically fit, we would like to scale this, but we don't want to scale it by taking everyone's data. We would just like to scale this to the healthy individuals, because then we can learn how much the individuals with the disease can be different from this. So what we do for that is that we are taking this fit transform function and we're splitting it into two. So here I'm again calling the pre-processing function and using the standard scaler. I'm only fitting. So once I only call the fit function but not fit transform, then I only have the scalar object. And this object, we can then use it to transform any kind of data. So here I'm, as you can can see I'm calling the same data, but we can think of it as X healthy and X sick. So this will be then the scaled version of everyone. So a subset of that too. Does this make sense? I know it's a little bit. Like yes, you need to be able to know what's healthy or not in this case, right? Like if you have a lot of data, then if you want to scale it with respect to something, let's say in my thesis I have wild type yeast and I have yeast with gene. I always scale my data with respect to a wild type yeast. Okay, so what I do when I use fit, I always put the wild type data, and then I'm transforming all of the data. So I don't call a subset, but I'm transforming all of the data based on a subset of the data. Does that make sense?
Yeah, I guess I don't understand what happens if you, or what's the negative part of scaling.
Negative?
If you do both your wild type yeast and your what's the...
It may reduce the difference of the sick individuals in the data.
So you look at the data as a broader variation.
Yes, and this comes to the assumption that the normal individuals and sick individuals have different kind of means, right? If they have the same means, then this would be a redundant step. But let's say if you have different means, then if you want to scale all of them together, then, I mean, this is just something that I'm in my work and it works fine, but it may be totally unnecessary too. So, and you may want to also like that, and you may have new data sets coming up and you don't want to deal with scaling it again, then you can also call this too. So it just gives you a modularity in this case. Okay, so now we just, here I'm again using the same plotting function 4 ways to see how the scaled data looks like, and we will see that it won't look any different from the normal data. So we can go over that. But again, if you have different kind of units in the features, then the scaled version will look completely different. Okay.
So your axes have changed, right?
I mean, the axis, sorry, like the data. But if you want to do later on with the scaled data, that will also affect everything else. So, okay. So here I'm again using. So now I'm doing both scaling and PCA, and this will again look the same. So I won't go into this, but just briefly, I'm using the scaled data and the same PCA function, and I'm plotting it. Okay. So here I also plotted the one scale before, and as you can see, they look pretty much. So this was, again, an unnecessary step, but just to show that. Also, what I would like you to appreciate here is that the PC1 range is from -3 to 4, and then PC2 is from -1 to 1. So we can see what kind of spread the PC1 and 2 has. So PC1 explains 92% of the variance in the data by just these standards. But if we have the same fixed limits with this, then all of the data sets, all of the data points will just be very close together. With the let's say that x limit will be the same, and then we can do -3 and 3. And then so the okay, this didn't change that much, but so with the scale data set, we see that it has a wider, the data points are more spread apart from each other. Scaled version, they're more close. This may, this kind of, the data points that are close together can be, sorry, this way of visualizing the data or pre-processing the data may be better for some of our algorithms, because here we are kind of forcing the data to be spread apart, right? Because the one on the right is what the raw data looks like, and we are doing all of the scaling and PCA process to make them more spread apart, but this will probably help us more in the following learning steps too. Okay, so let's just, and this is again the same thing, so I won't go into detail. Okay, so here now we want to do some kind of a classification. And most of the classification algorithms take binary targets, but there are a lot of multi-class algorithms too. So what I mean by that is that most of the algorithms either have a 1 or 0 for their targets, and that's why I'm just taking the iris data set and I'm just picking the 2 species rather than 3. So I just want to have a binary data set with this one. And then what I'm doing here is that I got rid of the third species, and I'm just plotting them here, just to visualize. So we have 2 classes, and we want to apply some classification algorithms to it. So the main, the most basic algorithm to use for binary classification is, although they have the regression terms in their names, it can still be applied to be a classification task. So here we're calling scikit-learn's linear model, and we're calling the linear regression function here. So even though it's a linear regression function, we're still trying to find a decision boundary. Let's say like a decision boundary here that would cut the data into 2 by having a line here. And then whatever that's above the line will be classified as blue, and whatever below will be classified as red. And then the same can be applied to here too, if we think that we have 2 features, obviously. But if we have more features, then this line will be a hyperplane in the high dimensions. Okay, so again, as how I have been calling PCA too, now I'm calling the linear regression model from the linear model function. And the LR stands for the model of my name. And then I'm using the model name to fit the data. So the data now is iris2, and this is the 2-class version of iris. And I changed the target name into y2. So once I fit the data in the model, then this means that we have found the decision boundary and how to do the classification test. So it's just these 2 steps that we can come up with the decision boundary. And then we are using the predict function in order to predict the data set. So here, I'm just calling the predict function, and I'm taking the predicted values for the targets. So it will be 0 or 1. Then we're using, again, the models, one of the models method called score, and we're feeding in the data and then the actual targets. And then sorry, this is, okay. So with the score, it looks at this data set, and then it predicts, and then it calculates. So with the score function, so here we're not using the ypred in order to calculate the score, but this is what it's doing. So in the score function, it's also doing the prediction function before. So it may seem redundant, but it will make more sense once I talk about the cross-validation method. So here the accuracy is 96%. So in the 2-class version of the iris dataset, we can achieve this accuracy. And there's also another method called logistic regression. And instead of finding a decision boundary between data points, it finds a probability for each data point to belong to a class. So it's just the difference between those 2. And we can still do the same thing. and then the accuracy turns out to be 1. So it's better than a linear regression. Okay, so, and then I'm just here, I only put like the different kind of data manipulations we did earlier as the, so this is, I'm just taking the first 2 features. I have the scaled version, I have the PCA version, and you can play around with how the accuracy will change with that too. But what I would like you to appreciate here is that instead of having 2 classes, we have all of the classes. So we have 3 classes. And I'm again calling the logistic regression model. And here I'm defining that it will be multi-class, and I'm using a multinomial parameter in order to do that. I don't know what these 2 hyperparameters stands for, but you can of course read the documentation. And then with that, I'm again fitting this linear, I'm fitting my model into X and Y, the data and the target. And then I'm predicting and I'm calculating the score. So here, once we have 3 classes, by using logistic regression, we can still achieve 97% accuracy. So that's pretty good. Yes.
The reason you didn't split it into test and train.
It's just for to like first learn. This will never be the case. So now we have to talk about cross-validation, because what's happening here, although we seem to have really great accuracies, what we're doing is kind of like cheating, right? Because if you take a look at this bar, all of this bar stands for the data that has targets. And what we're doing is that we're trying to learn a model by using all of this data, and then we're predicting all of this data again, but we have already seen it before, right? So it's not actually learning. So in order to, and then this will also lead to overfitting in the future too. So in order to not do that, we have to split the data into 2 or 3 parts. So if you want to split the data, we want to have a bigger portion that's called the training set, and we only use this portion to learn the model, to learn the decision boundary, to learn all of the functions that we do the classification with. And now we're setting aside the test set in order to see how our performance is with the data that we haven't seen before, right? And people usually split it into 80 and 20%, but you can play around with it too. And there's also another technique called cross-validation. So this was one-fold cross-validation. There's another method called k-fold cross-validation. And there are multiple ways that you can do this split, right? It just doesn't have to be like that. And what people do is actually, they just take the 20%, and then they change the training set and test set, and then they keep changing it until they can cover all of the data set like that. And then they report all of the different accuracies, and they usually report the average of those. So it's called cross-validation. Okay, so how are we going to split the training and test set? So you can just do it manually too, or scikit-learn model selection function has another function called train and test split. And this is really easy to use. So it returns 4 different data sets. So it's the training data, test data, and training targets and test targets. And then we're calling the train test split function. And then we're calling all of the data and all of the targets. So it just does the split for us. And then here I'm printing the target and test set sizes. And then I'm again calling the logistic regression. But what's different with this one is that I'm fitting the model based on only the training data. So I have the training data and the training targets. I'm fitting the model, and then I'm predicting based on the test set. So this will be the predicted score will be only on the test set, and then I'm scoring this based on the, again, the test set. So k-fold is not here, sorry. It's somewhere below, but we'll go into that. So this is just how the data set sizes, and still we have a really high accuracy for when we set aside the 20% too, because with logistic regression multi-class, we can learn really good. Okay, and with that, if you have multiple classes, and you have predictions on that, you may want to report this by using your confusion matrix. So I'm again using scikit-learn matrix function and from that confusion matrix. And then here it's just a simple little function that I found online to do this confusion matrix in a nice way. And for that, I've already used the logistic regression model earlier. So I have the actual targets and predicted targets. So these two are what we need for the confusion matrix. And these will be just two lists for each sample, what's the actual and what's the predicted target. And then it will calculate the values based on that. Okay, so let's just run this. So here we can see that the true labels are here, and then the predicted labels are here. And we have 100% accuracy, and we can classify all of these test samples correctly using that. Okay, so here now, this is where we're going to do the cross-validation. So again, we're splitting the data into, I've been doing this for 40, but we can do a 20% test data. And what I'm doing here is that now, instead of calling a logistic regression function, I'm calling another supervised learning method called support vector machines. And it basically does, in this data set, that it finds linear boundaries between three classes. So if I'm just going to go up here in our data set, so it just tries to find linear ways of how to do this. It doesn't have to be linear, but basically it finds boundaries that will maximize the distances between the data points here. So it's kind of like linear regression, but it just cares more about the data points from different classes that are close together. So you can read more about support vector machines. They're widely used. So we are using that. And here I've been saying that it's a linear way of doing it, but you can have non-linear way of doing it too by changing the kernel here, and you can read the documentation. And this support vector machine is again from the scikit-learn package, and we're again fitting it by the training set, and then we're predicting on the test set. Okay. And then here I also did this in one-fold cross-validation accuracy, so it's 1. And then with 5-fold cross-validation accuracies, I've been taking different chunks of the test set for these for the 5-fold cross-validation. And what people usually report is the average of all of these 5 accuracies right here. So, okay. Is there any questions so far? All right. So this is another data set that has images in it, and it's okay. Sorry.
So you do 5-fold cross-validation no matter your test training split? So
no, you can do as many as you want, but with 5-fold, if you have, let's say, if you have 5-fold and you separate the data into 20%, it will be like the 20 here, % here, and then the 80 here, and 20. Yes, so they will be different. But let's say if you want to do, again, 20% test set, but like 10-fold, there will be some overlapping data points in your test. But it won't be a problem because you won't see the test set anyways, right? It will be even further validation of the performance.
Could I do something like 1%?
Then you wouldn't be able to capture like that, right? Yeah. Okay, so this is another data set that consists of handwritten digits. And just to visualize what the data looks like, it has 64 pixels, and there are 1,800 images that cover all of these numbers. So what we are doing is we're applying what we have learned before, and it's the same way. We're again separating the training and test set. Here I just put the logistic regression, but we also have the SVM here that I commented out, so you can play around with both of that. We're again fitting this model based on the training data set, and it on test set.
Yeah.
Why the which one is so?
Mine is perfect.
Because so from the old version, it doesn't have the split. So I deleted that cell altogether. So maybe I will do the pull request here. So that's when I first showed that it's perfect classification, but it's because of this cheating, right?
So it's putting in the test code line that makes it so it's not.
Yes. So it's not. There are a couple of wrong predictions here, but it's still pretty good, right? It's still 95%, but we can still do some kind of misclassification. So it's just a way of visualizing that too. Okay, so far we have been talking about the classification test, the supervised learning case where we know the targets. Well, what if you're interested in finding underlying groups, right? What if we don't even know what the targets are? We just want to learn how to group the data into a more meaningful sense. So here where we are using k-means, and k-means is an algorithm in the scikit-learn cluster function. And here, please, I just put this target here so that we can compare the clustering results with the actual target. So it's not a way to validate if the clustering is working good or not, because in the real world, you won't know the targets, and that's why you're doing clustering in the first place. But this is just a way to show how this clustering is working. So what k-means is doing is that you have, although it's an unsupervised learning problem, there's a little bit of trick here because we have to specify the number of clusters. There are different ways of coming up with the best number of clusters that have in the data. And you can check Bayesian information criteria for that, or BIC. I'm not going to go into detail here, but we kind of know already how many groups we need to see from the data. And then, so I'm just using that. And then there are different kinds of initializations that you can look at it. And then we're fitting and predicting this data set. So we have been fitting and predicting on test data set, but we don't have that. So we're doing in just one line fit predict, and then we can then visualize the cluster centers. So this doesn't have any output, but we have, so what I have is the Y predicted values and cluster centers. So this will be important for us. Okay, so what I'm doing here is that this will be a weird looking confusion matrix. It's not a confusion matrix, but I also changed this version from the old one. So here on the, again, y-axis, we have the true labels, and then on the x-axis, we have the cluster assignments. And although this looks weird, it is because when we do the clustering, it doesn't know if setosa is cluster 0 or versicolor is 1, right? It just randomly gives a number. So just, although this accuracy here makes no sense, I should probably delete this accuracy title here. So please ignore this accuracy. But here, what we need to see is that we have a lot of versicolors that we identify with the 0 cluster, with the first cluster, but we do some kind of, so maybe we should focus on the last one here, right? So with this Virginica, we're clustering it into 2 different groups. So we, so in the clustering, we can find the groups of the 2 species really good, but this one kind of, we don't know what we're going to put it. So it's just a way to see how the clustering method can be worked. So, but what people usually do is that they only have the cluster assignment, so that they will just define the groups themselves. And if we didn't know the targets already, then we only rely on the BIC.
And plug in differences by the labels that
The labels?
colors.
I need to take a couple of minutes to plot that, but I can edit to the notebook, and then I can pull request after that, so you can see that too. Okay, so I can go into the regression just briefly if you want. We're kind of out of time, or I can focus on the teapot package that I taught before. So which one would be better? So I think it will be better because we have been also talking about the linear regression. This is what I'm also doing, I guess. Also under supervised learning. But instead of classifying it into different classes, we want to predict a number. So let's say, so the data set that I put for the regression problem is Boston housing prices. So it has 13 different features with continuous values. And we want to use regression algorithms in order to come up with the housing prices. So it's not a class, but it's just a price. And you can, again, follow it the same way. I'm doing PCA and then the linear regression model. And then I'm calculating the score. So I won't go into detail. Okay. There's a really cool package with that's called Teapot, and this is outside of scikit-learn, I assume. So what it does is that you have a data and you have some targets. And what Teapot does is that it finds the optimum algorithm that will do a kind of certain task for you. So what it does is that it does all of the data cleaning, feature selection, pre-processing, and model selection. So it tries different kinds of models, and then it comes up with the one that has the highest accuracy. So okay, so here, the Teapot package, you can load it, you can install it from here. And then I'm again calling the iris data set. And then so what it does is that it outputs a script that you can run on your data. So you don't even need to go and like, look, how do I do this algorithm or not, if you just want to do a simple task. Yes, it does, and it exports it too. Yeah. So again, we're doing a training and test set, and we have to do it always. You don't want to cheat. And then there are a couple of, so here, instead of like calling SVM or like linear regression, we're calling Teapot classifier. And then there's also a Teapot regressor and in this following cell. So again, I'm calling that, and there are a couple of different hyperparameters that I have no idea of, but you can look at the documentation. And again, we're calling it with the function, and we're fitting in with the training data, and then we're scoring it with the test data, and then we're exporting. So let's see how this runs. So it's doing some kind of optimization, and I hope.
Why are they called hyperparameters?
I knew about that, but now I can't recall why.
Is it always like that?
Like, did you hear hyperparameters outside of like machine learning? It's usually referred as such. I don't know why. Yeah.
It's because often they use machine learning parameters for whatever thing they're learning on. So the hyperparameters, yeah, that's that.
Like the parameters would be the data and targets, right? Mm-hmm. And then the like other stuff that we put are yeah. Mm-hmm. So this is pretty slow, but I just want to show you what the output script looks like. And then once it's running, we can just go over this briefly. So if you have a data set that you want to do regression on, so you don't care about the classes, but you want to do regression problem. So here I have the Boston data set. And then again, I'm using everything as the same way. And yeah, I do have the targets here. Yes, because it's supervised. And then I'm doing the training and test set. And instead of calling Teapot classifier, I'm calling Teapot regressor. And this will do the same thing. So yeah, this is a little slow. But
I can ask another question.
Yes.
So you only do it with when you know your labels. Could I do it with some unsupervised classifier?
I'm not sure about it because it.
But then you can evaluate the so
yes. Yeah, I'm. With the examples here, it's usually classification, digit recognition. So it's again classifier, and then regression, Titanic survival. So these are all supervised versions of it, but it doesn't say, yeah. And it's using genetic programming to find the optimum. I don't think it does any kind of, because with the unsupervised learning, if you have like clustering, then there's not really much to, like, how do you assess if the clustering is good or not, right? If you don't know the labels.
Yeah, we want to implement that to check.
Yes, like you need to check yourself, or you can, with like k-means or any kind of specific stuff, you can change like the number of clusters and then calculate the BIC. So it's always a good way. So okay, it printed out the script here. So this is what the teapot outputs as a script, and this is ready to go. So you can load the data, and then here, well, it does the training and test split again as the way we were doing. And then here, the best classification function teapot found is decision tree classifier. So it's one of the algorithms. It's probably also called random forest. I'm not sure, but maybe it's a simpler version of random forest. So it's just another algorithm that does classification. Apparently, Iris dataset is best with this. And then it fits and predicts everything. So this just automatically gives you all of the script that you need to do the task. And here, again, the current best internal cross-validation scores 98%. And we achieved even higher with logistic regression before. So yeah, that's pretty much it. Thank you for listening.